Now we will talk about the divergence in curvilinear coordinate systems, but before we do that, let's recall our physical picture of the divergence. So here we have considered a differential volume in which we have basically total number of particles capital N in d tau, which is rho d tau, where we have the particle density. And by looking at the divergence, we have found the following results. So let's recall that. The divergence of J is basically the divergence of the current, the flux of particles. So if the divergence of a vector field is positive in a region, then that region is a source. Field lines are born in that region. If the divergence of a vector field is negative in a region, then that region is a sink. Field lines are terminated. If the divergence of a vector field is zero, then all field lines that enter it must leave that region. So that's what we have found out. Okay, now let's consider the integral definition of the divergence to figure out what we should do in curvilinear coordinates. It is the limit as the area S and volume V goes to 0. We have the closed surface integral d sigma dot product with vector A divided by the volume integral d tau. So this was the integral definition of divergence. Now, if we look at as v goes to 0, the volume integral d tau, this is basically the differential volume that we have figured out. It is h1 dq1, h2 dq2, h3 dq3, so we can substitute that here. So for the differential volume, we have dq1, dq2, dq3, scale factors h1, h2, h3. And now we can work on the top of this ratio, the closed surface integral d sigma dot A. So for a differential volume, we're going to have a bottom surface, top surface, left, right, front, and back surface. So if you go back to this figure, we have top, bottom, left, right, front, and back. Okay, so for the bottom surface, we have already figured out how this should look like. We have h1 dq1, h2 dq2 multiplied by the component of the vector A on the q3 axis, but this has to point in minus q3 hat direction so that it points out of the surface. So we have for the bottom surface minus dq1, dq2, h1, h2, and the q3 component of the vector A, and the scale factors are evaluated at q1, q2, and q3. The bottom surface A vector is A3 q3 hat. So from the right-hand rule, we have found that this is basically we're taking the cross product of q1 and q2 that gives us a plus q3, but the area vector has a component a3 in q3 hat direction. So basically that's what we find here. So for the d sigma vector, the area vector, we have minus dq1, dq2, h1, h2, it's minus q3 hat direction, all evaluated at q1, coordinates q1, q2, q3. So this is what we have figured out from this figure here. So because we have the smallest coordinates values at this point. It contains the origin, so we have to evaluate the scale factors at the origin. Now, if I move to the top, two things will change. Now the area vector has to point in plus Q3 hat direction, and the evaluation should be performed at Q1, Q2, and Q3 plus dQ3. So let's do that. For the top surface, we have plus dQ1, dQ2, H1, H2, A3, the scale factors evaluated at Q1, Q2, Q3 plus dQ3, because it's the top surface. Now the area vector, d sigma, is going to point parallel to Q3 hat direction. So it's going to be, for the bottom it was anti-parallel. And the A3 vector also points parallel to Q3 vector. Now we have H1, H2, A3. So we have to evaluate this for H1, H2, A3, evaluated at Q1, Q2, Q3 plus dQ3, where dQ3 is small. We can use the Taylor series expansion. So we can say first set dQ3 to 0. So the first term we have H1, H2, A3 evaluated at Q1, Q2, Q3. And then we have to take the partial derivative of H1, H2, A3 with respect to Q3, evaluate this at Q1, Q2, Q3, and multiply it by dQ3. So this is basically saying when dQ3 is small, we have this approximation for the product H1, H2, A3 using Taylor series expansion. Now, if I add the two contributions, now I have from the top this term, and from the bottom I have this term minus dQ1, dQ2, H1, H2, A3. And then here I will have plus dQ1, dQ2, H1, H2, A3. So these first terms will cancel out. I will be left with this term only. So the bottom and top contributions give me partial derivative of H1, H2, A3 with respect to Q3 evaluated at Q1, Q2, Q3. Now this has multiplied by dQ3. The area gives me dQ1, dQ2. So this is dQ1, dQ2, dQ3. Okay, so this is what the top and bottom surfaces give me. Now, if I consider left, right, front, and back surfaces as well, I can do the similar calculations, and I will end up with the following. Now, instead of H1, H2, first I'm going to have partial derivative of H2, H3, A1 with respect to Q1. And then I will have, so which surfaces will give me this contribution? Let's take a look. H2, H3, so the left and the right surfaces will give me this contribution. Then I will have front and back surfaces, H1, H3, A2, partial derivative with respect to Q1. Then I will have partial derivative of H1, H2, A3. These are the bottom and top surfaces giving me this contribution. So this was Q2, this is now Q3, multiplied by dQ1, dQ2, dQ3. All right. So the top of this ratio, closed surface integral, d sigma dot A gives me this contribution. The bottom, which is d tau, integral v goes to 0 as v goes to 0 d tau, is d tau basically. dq1, dq2, dq3, h1, h2, h3. So these will cancel, and I will have 1 over h1, h2, h3 remaining here. Therefore, the divergence of A in curvilinear coordinate system is found by looking at this ratio 1 over h1, h2, h3. Then I will have partial derivative of h2, h3, a1 with respect to q1, partial derivative of h1, h3, a2 with respect to q2, and partial derivative of h1, h2, a3 with respect to q3. And this is going to give me the final result for the divergence of vector A in the curvilinear coordinate system. Okay, so let's take a look at what we did here. First, I wanted to recall the meaning of divergence. The divergence being positive implies that I have a source of field lines, divergence being negative sink of field lines, divergence being 0. The number of field lines entering a region is equal to the number of field lines leaving the region, and the integral definition of divergence is limit as S and V go to 0, closed surface integral d sigma dot A divided by the volume integral d tau. So this is basically area vector, differential area vector dot product with vector A. So for the differential volume part, we have already found previously that d tau is h1, h2, h3, dq1, dq2, dq3. For the closed surface integral d sigma dot A, I have to consider bottom, top, left, right, front, and back surfaces. And for each of them, the area vector has to point normal to the surface, pointing in the outwards direction. So by looking at the bottom contribution, for example, I have realized that this area is given by h1, h2, dq1, dq2. The area vector must point in minus q3 hat direction. So I have minus dq1, dq2, h1, h2. I'm taking the dot product with the area, so because it's in minus q3 hat direction, this is a3. So minus q3 hat dot product with A gives me the A3 component, and this has to be evaluated at Q1, Q2, Q3. So that's what I have here for the bottom surface. Now for the top surface, I have the same thing, but this has to be evaluated at Q3 plus dQ3, and also it has to be positive because the area vector has to point in plus Q3 hat direction. Now I considered this H1, H2, A3 product written at the point Q1, Q2, Q3 plus dQ3. In the limit dQ3 goes to 0 using Taylor series expansion, it's equal to H1, H2, A3 evaluated at Q1, Q2, Q3, which was the same contribution from the bottom surface, but I have the partial derivative with respect to Q3 multiplied by dQ3. Taylor series expansion as dQ3 goes to 0. So putting the top and bottom together, so this is the top, this is the bottom together, minus dQ1, dQ2, H1, H2, A3. And then I will have plus dQ1, dQ2, H1, H2, A3. from this part. So this is going to give me a cancellation. So this is going to be left out. So I will have this partial derivative dq3, dq1, dq2. So this is going to be the end result. For left, right, front, and back surfaces, the same thing, similar results apply. For each of them, if I'm taking derivative with respect to Q1, it's A1 and H2, H3. If taking derivative with respect to Q2, it's A2, H1, H3, etc. And dividing it by the differential volume, which is H1, H2, H3, dQ1, dQ2, dQ3, I'm left with 1 over H1, H2, H3, partial derivative with respect to Q1, H2, H3, A1, partial derivative with respect to Q2 of H1, H3, A2, and partial derivative with respect to Q3 of H1, H2, A3.